Mathematical physics refers to development of mathematical methods for application to problems in physics. The Journal of Mathematical Physics defines the field as the application of mathematics to problems in physics and the development of mathematical methods suitable for such applications and for the formulation of physical theories. Scope: there are several distinct branches of mathematical physics, and these roughly correspond to particular historical periods. Classical mechanics. The rigorous, abstract and advanced reformulation of Newtonian mechanics adopting the Lagrangian mechanics and the Hamiltonian mechanics even in the presence of constraints. Both formulations are embodied in the so-called analytical mechanics. It leads, for instance, to discover the deep interplay of the notion of symmetry and that of conserved quantities during the dynamical evolution, stated within the most elementary formulation of Noether's theorem. These approaches and ideas can be and, in fact, have been extended to other areas of physics as statistical mechanics, continuum mechanics, classical field theory and quantum field theory. Moreover, they have provided several examples and basic ideas in differential geometry. Partial differential equations. The theory of partial differential equations are perhaps most closely associated with mathematical physics. These were developed intensively from the second half of the 18th century until the 1930s. Physical applications of these developments include hydrodynamics, celestial mechanics, continuum mechanics, elasticity theory, acoustics, thermodynamics, electricity, magnetism, and aerodynamics. Quantum theory. The theory of atomic spectra developed almost concurrently with the mathematical fields of linear algebra, the spectral theory of operators, operator algebras and more broadly, functional analysis. Non-relativistic quantum mechanics includes Schrödinger operators, and it has connections to atomic and molecular physics. Quantum information theory is another subspecialty. Relativity and quantum relativistic theories. The special and general theories of relativity require a rather different type of mathematics. This was group theory, which played an important role in both quantum field theory and differential geometry. This was, however, gradually supplemented by topology and functional analysis in the mathematical description of cosmological as well as quantum field theory phenomena. In this area both homological algebra and category theory are important nowadays. Statistical mechanics. Statistical mechanics forms a separate field, which includes the theory of phase transitions. It relies upon the Hamiltonian mechanics and it is closely related with the more mathematical ergodic theory and some parts of probability theory. There are increasing interactions between combinatorics and physics, in particular statistical physics. Usage. The usage of the term mathematical physics is sometimes idiosyncratic. Certain parts of mathematics that initially arose from the development of physics are not, in fact, considered parts of mathematical physics, while other closely related fields are. For example, ordinary differential equations and symplectic geometry are generally viewed as purely mathematical disciplines, whereas dynamical systems and Hamiltonian mechanics belong to mathematical physics. Mathematical versus theoretical physics. The term mathematical physics is sometimes used to denote research aimed at studying and solving problems inspired by physics or thought experiments within a mathematically rigorous framework. In this sense, mathematical physics covers a very broad academic realm distinguished only by the blending of pure mathematics and physics. Although related to theoretical physics, mathematical physics in this sense emphasizes the mathematical rigor of the same type as found in mathematics. On the other hand, theoretical physics emphasizes the links to observations and experimental physics, which often requires theoretical physicists to use heuristic, intuitive, and approximate arguments. Such arguments are not considered rigorous by mathematicians. Arguably, rigorous mathematical physics is closer to mathematics, and theoretical physics is closer to physics. This is reflected institutionally. Mathematical physicists are often members of the mathematics department. Such mathematical physicists primarily expand and elucidate physical theories. Because of the required level of mathematical rigor, these researches often deal with questions that theoretical physicists have considered to already be solved. However, they can sometimes show that the previous solution was incomplete, incorrect, or simply too naive. Issues about attempts to infer the second law of thermodynamics from statistical mechanics are examples. Other examples concerns all the subtleties involved with synchronization procedures in special and general relativity. The effort to put physical theories on a mathematically rigorous footing has inspired many mathematical developments. For example, the development of quantum mechanics and some aspects of functional analysis parallel each other in many ways. The mathematical study of quantum mechanics, quantum field theory and quantum statistical mechanics has motivated results in operator algebras. The attempt to construct a rigorous quantum field theory has also brought about progress in fields such as representation theory. Use of geometry and topology plays an important role in string theory. Prominent mathematical physicists, before Newton, the roots of mathematical physics can be traced back to the likes of Archimedes in Greece, Ptolemy in Egypt, Alhazen in Iraq, and al-Biruni in Persia. In the first decade of the 16th century, amateur astronomer Nicolaus Copernicus proposed heliocentrism, and published a treatise on it in 1543. Not quite radical, Copernicus merely sought to simplify astronomy and achieve orbits of more perfect circles, stated by Aristotelian physics to be the intrinsic motion of Aristotle's fifth element the quintessence or universal essence known in Greek as aether for the English pure aira that was the pure substance beyond the sublunary sphere, and thus was celestial entities' pure composition. The German Johannes Kepler, 1571–1630, Tycho Brahe's assistant, modified Copernican orbits to ellipses, however, formalized in the equations of Kepler's laws of planetary motion. An enthusiastic atomist, Galileo Galilei in his 1623 book The Essay asserted that the book of nature is written in mathematics. His 1632 book, upon his telescopic observations, supported heliocentrism. Having introducing experimentation, Galileo then refuted geocentric cosmology by refuting Aristotelian physics itself. Galilei's 1638 book Discourse on Two New Sciences established law of equal free fall as well as the principles of inertial motion, founding the central concepts of what would become today's classical mechanics. By the Galilean law of inertia as well as the principle Galilean invariance, also called Galilean relativity, for any object experiencing inertia, there is empirical justification of knowing only its being at relative rest or relative motion rest or motion with respect to another object. René copyright Descartes adopted Galilean principles and developed a complete system of heliocentric cosmology, anchored on the principle of vortex motion, Cartesian physics, whose widespread acceptance brought demise of Aristotelian physics. Descartes sought to formalize mathematical reasoning in science, and developed Cartesian coordinates for geometrically plotting locations in 3D space and marking their progressions along the flow of time. Newtonian and post-Newtonian, Isaac Newton, 1642–1727, developed new mathematics, including calculus and several numerical methods such as Newton's method to solve problems in physics. Newton's theory of motion, published in 1687, modeled three Galilean laws of motion along with Newton's law of universal gravitation on a framework of absolute spatial hypothesized by Newton as a physically real entity of Euclidean geometric structure extending infinitely in all directions while presuming absolute time, supposedly justifying knowledge of absolute motion, the object's motion with respect to absolute space. The principle Galilean invariance relativity was merely implicit in Newton's theory of motion. Having ostensibly reduced Keplerian celestial laws of motion as well as Galilean terrestrial laws of motion to a unifying force, Newton achieved great mathematic rigor of theoretical laxity. In the 18th century, the Swiss Daniel Bernoulli, 1700–1782, made contributions to fluid dynamics, and vibrating strings. The Swiss Leonhard Euler, 1707–1783, did special work in variational calculus, dynamics, fluid dynamics, and other areas. Also notable was the Italian-born Frenchman, Joseph Louis Lagrange, 1736–1813, for work in analytical mechanics and variational methods. A major contribution to the formulation of analytical dynamics called Hamiltonian Dynamics was also made by the Irish physicist, astronomer and mathematician, William Rowan Hamilton, 1805–1865. Hamiltonian dynamics had played an important role in the formulation of modern theories in physics including field theory and quantum mechanics. The French mathematical physicist Joseph Fourier, 1768–1830, introduced the notion of Fourier series to solve the heat equation, giving rise to a new approach to handle partial differential equations by means of integral transforms. Into the early 19th century, the French Pierre-Simon Laplace, 1749–1827, made paramount contributions to mathematical astronomy, potential theory, and probability theory. Simon copyright on Denis Poisson, 1781–1840, worked in analytical mechanics and potential theory. In Germany, Carl Friedrich Gauss, 1777–1855, made key contributions to the theoretical foundations of electricity, magnetism, mechanics, and fluid dynamics. A couple of decades ahead of Newton's publication of A Particle Theory of Light, the Dutch Christiaan Huygens, 1629–1695, developed the wave theory of light, published in 1690. By 1804, Thomas Young's double-slit experiment revealed an interference pattern as though light were a wave, and thus Huygens's wave theory of light, as well as Huygens's inference that light waves were vibrations of the luminiferous ether, was accepted. Jean-Augustin Fresnel modeled hypothetical behavior of the ether. Michael Faraday introduced the theoretical concept of a field not action at a distance. Mid-19th century, the Scottish James Clerk Maxwell, 1831–1879, reduced electricity and magnetism to Maxwell's electromagnetic field theory, whittled down by others to the four Maxwell's equations. Initially, optics was found consequent of Maxwell's field. Later, radiation and then today's known electromagnetic spectrum were found also consequent of this electromagnetic field. The English physicist Lord Rayleigh, 1842–1919, worked on sound. The Irishman William Rowan Hamilton, 1805–1865, George Gabriel Stokes, 1819–1903, and Lord Kelvin, 1824–1907, did a lot of major work. Stokes was a leader in optics and fluid dynamics. Kelvin made substantial discoveries in thermodynamics. Hamilton did notable work on analytical mechanics, finding out a new and powerful approach nowadays known as Hamiltonian mechanics. Very relevant contributions to this approach are due to his German colleague Carl Gustav Jacobi, 1804–1851, in particular referring to the so-called canonical transformations. The German Hermann von Helmholtz, 1821–1894, is greatly contributed to electromagnetism, waves, fluids, and sound. In the United States, the pioneering work of Josiah Willard Gibbs, 1839–1903, became the basis for statistical mechanics. Fundamental theoretical results in this area were achieved by the German Ludwig Boltzmann, 1844–1906. Together, these individuals laid the foundations of electromagnetic theory, fluid dynamics, and statistical mechanics. Relativistic, by the 1880s, prominent was the paradox that an observer within Maxwell's electromagnetic field measured it at approximately constant speed regardless of the observer's speed relative to other objects within the electromagnetic field. Thus, although the observer's speed was continually lost relative to the electromagnetic field, it was preserved relative to other objects in the electromagnetic field. And yet no violation of Galilean invariance within physical interactions among objects was detected. As Maxwell's electromagnetic field was modeled as oscillations of the ether, physicists inferred that motion within the ether resulted in ether drift, shifting the electromagnetic field, explaining the observer's missing speed relative to it. physicists' mathematical process to translate the positions in one reference frame to predictions of positions in another reference frame, all plotted on Cartesian coordinates, had been the Galilean transformation, which was newly replaced with Lorentz transformation, modelled by the Dutch Hendrik Lorentz, 1853–1928. In 1887, experimentalists Michelson and Morley failed to detect ether drift, however. It was hypothesized that motion into the ether prompted ether's shortening too, as modelled in the Lorentz contraction. Hypotheses at the ether thus kept Maxwell's electromagnetic field aligned with the principal Galilean invariance across all inertial frames of reference, while Newton's theory of motion was spared. In the 19th century, Gauss's contributions to non-Euclidean geometry, or geometry on curved surfaces, laid the groundwork for the subsequent development of Riemannian geometry by Bernhard Riemann, 1826–1866. Austrian theoretical physicist and philosopher Ernst Mach criticized Newton's postulated absolute space. Mathematician Jules-Henri Poincaré, copyright, 1854–1912, questioned even absolute time. In 1905, Pierre Duhem published a devastating criticism of the foundation of Newton's theory of motion. Also in 1905, Albert Einstein, 1879–1955, published Special Theory of Relativity, newly explaining both the electromagnetic field's invariance and Galilean invariance by discarding all hypotheses at ether, including ether itself. Refuting the framework of Newton's theory absolute space and absolute mere special relativity states relative space and relative time, whereby length contracts and time dilates along the travel pathway of an object experiencing kinetic energy. In 1908, Einstein's former professor Hermann Minkowski modeled 3D space together with the 1D axis of time by treating the temporal axis like a fourth spatial dimension altogether 4D spacitum and declared the imminent demise of the separation of space and time. Einstein initially called this superfluous learnedness, but later used Minkowski space-time to great elegance in general theory of relativity, extending invariance to all reference frames whether perceived as inertial or as accelerated and thanked Minkowski, by then deceased. General relativity replaces Cartesian coordinates with Gaussian coordinates, and replaces Newton's claimed empty yet Euclidean space traversed instantly by Newton's vector of hypothetical gravitational force an instant action at a distance with a gravitational field. The gravitational field is Minkowski spacetime itself, the 4D topology of Einstein ether modeled on a Lorentzian manifold that curves geometrically, according to the Riemann curvature tensor, in the vicinity of either mass or energy. Quantum, another revolutionary development of the 20th century, has been quantum theory, which emerged from the seminal contributions of Max Planck, 1856–1947, and Einstein's work on the photoelectric effect. This was, at first, followed by a heuristic framework devised by Arnold Sommerfeld, 1868–1951, and Niels Bohr, 1885–1962, but this was soon replaced by the quantum mechanics developed by Max Born, 1882–1970, Werner Heisenberg, 1901–1976, Paul Dirac, 1902–1984, Erwin Schrödinger, 1887–1961, Satyendranath Bose, 1894–1974, and Wolfgang Pauli, 1900. 1958. This revolutionary theoretical framework is based on a probabilistic interpretation of states, and evolution and measurements in terms of self-adjoint operators on an infinite-dimensional vector space. That is the so-called Hilbert space, introduced in its elementary form by David Hilbert, 1862–1943, and Frigyes Rice, 1880–1956, and rigorously defined within the axiomatic modern version by John von Neumann in his celebrated book on mathematical foundations of quantum mechanics, where he built up a relevant part of modern functional analysis on Hilbert spaces, the spectral theory in particular. Paul Dirac used algebraic instructions to produce a relativistic model for the electron, predicting its magnetic moment and the existence of its antiparticle, The positron. List of important mathematical physicists in the 20th century. Prominent contributors to the 20th century's mathematical physics include Arnold Sommerfeld, 1868–1951, Albert Einstein, 1879–1955, Max Born, 1882–1970, Niels Bohr, 1885–1962, Hermann Weyl, 1885–1955, Satyendranath Bose, 1894–1974, Wolfgang Pauli, 1900–1958, Werner Heisenberg, 1901–1976, Paul Dirac, 1902–1984, Eugene Wigner, 1902–1995, John von Neumann, 1903–1957, Shinichiro Tomonaga, 1906–1979, Hideki Yukawa, 1907–1981, Lev Landau, 1908–1968, Nikolai Bogolubov, 1909–1992, Mark Kac, 1914–1984, Julian Schwinger, 1918–1994, Richard Feynman, 1918–1988, Arthur Strong Whiteman, 1922–2013, Chen-Ning Yang, 1922 Rudolf Haag, 1922 Freeman Dyson, 1923 Martin Xiller, 1925 2014, Abdus Salam, 1926 1996, Jawan Kortara Gen Moser, 1928 1999, Peter Higgs, 1929 Michael Atiyah, 1929 Joel Lebowitz, 1930 Roger Penrose, 1931 Elliot H. Lieb, 1932 Sheldon Lee Glashow, 1932 Steven Weinberg, 1933 Ludwig D. Faddeev, 1934 David Rule, 1935 Yakov G. Sinai, 1935 Vladimir Arnold, 1937 2010, Arthur Jaffe, 1937 Roman Jackie, 1939 Leonard Susskind, 1940 Rodney J. Baxter, 1940 Stephen Hawking, 1942 Alexander M. Polyakov, 1945 Barry Simon, 1946 John L. Cardy, 1947 Edward Witten, 1951 and Juan M. Moldesiner, 1968 See also, International Association of Mathematical Physics, Notable Publications in Mathematical Physics, Notes. References, Zulso, Eric, Physmatics, A.R. Ziv, Physics/0506153, Bibcode, 2005 Physics. 6153 ZAR, Further Reading, The Classics. Abraham, Ralph. Marston, Gerald E., Foundations of Mechanics, A Mathematical Exposition of Classical Mechanics with an Introduction to the Qualitative Theory of Dynamical Systems, Providence, R.I. AMS Chelsea Pub, ISBN A978-0-8218-4438-0. Arnold, Vladimir I. Vogtman, K. Weinstein, A. Mathematical Methods of Classical Mechanics / Matematiczne metody klassyczno-mechaniki, New York, N.Y. Springer Verlag, ISBN A0-387-96890-3. Caron, Richard. Hilbert, David, Methods of Mathematical Physics, New York, N.Y. Interscience Publishers. Glim, James. Jaffe, Arthur, Quantum Physics, A Functional Integral Point of View, New York, N.Y. Springer Verlag, ISBN A0-387-96477-0. Haag, Rudolf, Local Quantum Physics, Fields, Particles, Algebras, Berlin, Germany A. New York, N.Y. Springer Verlag, ISBN A3-540-61049-9. Hawking, Stephen W. Ellis, George F. R., The Large-Scale Structure of Space-Time, Cambridge, England. Cambridge University Press, ISBN A0-521-20016-4. Kato, Toshio, Perturbation Theory for Linear Operators, Berlin, Germany. Springer Verlag, ISBN A3-540-58661. ZA edition of this title. Margenau, Henry. Murphy, George Moseley, The Mathematics of Physics and Chemistry, Huntington, N.Y. R.E. Krager Pub Company, ISBN A0-88275-423-8. Morse, Philip McCord. Festsch, Hermann, Methods of Theoretical Physics, Boston, Mass. McGraw-Hill, ISBN A0-07-043316. ZA edition of this title. Von Neumann, John. Baer, Robert T., Mathematical Foundations of Quantum Mechanics, Princeton, N.J. Princeton University Press. Reed, Michael C. Simon, Barry, Methods of Modern Mathematical Physics 4, New York City, Academic Press, ISBN A0-12-585001-8. Titchmarsh, Edward Charles, The Theory of Functions, London, England. Oxford University Press. Thering, Walter E. Harrell, Evans M., A Course in Mathematical Physics / Lubuch der Mathematischen Physik, New York, N.Y. Springer Verlage, Well, Herman. Robertson, H.P., The Theory of Groups and Quantum Mechanics / Gruppentheorie und Quantenmechanik, London, England. Methuen and Company. Whittaker, Edmund Taylor. Watson, George Neville, A Course of Modern Analysis, An Introduction to the General Theory of Infinite Processes and of Analytic Functions, with an account of the principal transcendental functions, Cambridge, Cambridge University Press, ISBN A978-0-521-58807-2A. Textbooks for Undergraduate Studies. ARFKEN, George B. Weber, Hans J., Mathematical Methods for Physicists, San Diego, CA. Academic Press, ISBN A0-12-059816-7. Boas, Mary L., Mathematical Methods in the Physical Sciences, Hoboken, N.J. John Wiley & Sons, ISBN A978-0-471-19826-0. Butkov, Eugene, Mathematical Physics, Reading, Mass. Addison Wesley, Jeffries, Harold. Swells Jeffries, Bertha, Methods of Mathematical Physics, Cambridge, England. Cambridge University Press. Cuss, Bruce R., Mathematical Physics, Applied Mathematics for Scientists and Engineers, Germany. Wiley VCH, ISBN A3-527-40672-7. Jews, Georg. Freeman, Ira M., Theoretical Physics, Dover Publications, ISBN A0-486-65227-0. Matthews, John. Walker, Robert L., Mathematical Methods of Physics, New York, N.Y. W. A. Benjamin, ISBN A0-8053-7002-1. Menzel, Donald Howard, Mathematical Physics, Dover Publications, ISBN A0-486-60056-4. Stackold, Ivor, Boundary Value Problems of Mathematical Physics, Philadelphia, PA. Society for Industrial and Applied Mathematics, ISBN A0-89871-456-7A. Textbooks for Graduate Studies. Hazani, Sadri, Mathematical Physics, A Modern Introduction to Its Foundations, Berlin, Germany. Springer Verlag, ISBN A0-387-98579-4. Reed, M. Simon, B. Methods of Mathematical Physics. Vol. 1-4. Academic Press. Teschl, G. Mathematical Methods in Quantum Mechanics. With applications to Schur paragraph Dingo operators. Providence, American Mathematical Society. ISBN A978-0-8218-4660-5. Moretti, V. Spectral Theory and Quantum Mechanics. With an Introduction to the Algebraic Formulation. Berlin, Milan, Springer. ISBN A978-88-470-2834-0A. Other specialized sub-areas. Islam, Jamal. Hussain, Fahim, Mathematical Physics Proceedings of the 12th Regional Conference, Islamabad, Pakistan, March 27 – April 1, 2006, Singapore, World Scientific, ISBN A978-981-270-591-4. Bayes, John C. Munian, Javier P., Gauge Fields, Knots, and Gravity, Singaporea. River Edge, N.J. World Scientific, ISBN A981-02-2034-0. Druk, Robert, Mathematical Physics, Chicago, IL. University of Chicago Press, ISBN A0-226-28862-5. Polyanin, Andre D., Handbook of Linear Partial Differential Equations for Engineers and Scientists, Boca Raton, FL. Chapman and Hall/CRC Press, ISBN A1-58488-299-9. Polyanin, Alexei D. Zaitsev, Valentin F., Handbook of Nonlinear Partial Differential Equations, Boca Raton, FL. Chapman and Hall/CRC Press, ISBN A1-58488-355-3. Sekiers, Peter, A Course in Modern Mathematical Physics, Groups, Hilbert Space and Differential Geometry, Cambridge, England. New York, N.Y. Cambridge University Press, ISBN A0-521-53645-6. Indurain, Francisco J., Theoretical and Mathematical Physics. The Theory of Quark and Gluon Interactions, Berlin, Germany. Springer, ISBN A978-36420699741-A.